we talked about fission yesterday, just the chemical, nuclear process. Everybody's watching up here, okay? We're going to go through some other stuff on the packet that you have in front of you in a minute. But this little picture kind of illustrates what's going on. All right, you basically have a uranium-235 nucleus. This is what's going on in any nuclear power plant. Yeah, well, not any one, but the ones up the road here that use U-235. You get a slow neutron that gets absorbed by that nucleus. It makes it unstable. It splits apart and gives off energy. It also gives off 2 more neutrons. Those neutrons get slowed down. They have to be slow neutrons. You might think that, well, the harder I hit them, the better. No. We want those neutrons to be absorbed by the nucleus, not just fly past it. We want them to be absorbed by them and therefore become unstable and split apart again. All right? Now, that's all well and good. What's our practical use for this? Well, 2, killing people. If we want to drop a bomb on people, we can kill them with this. All right? We can make a bomb out of this. That's one good reason to make nuclear. I mean, obviously, it's not a very good reason, but it's it's one of the reasons we've used for nuclear reactions. All right, to make nuclear weapons, atomic bombs. But obviously, a better one, a more peaceful one, would be what we have going on 5 miles up the road, the power plant. How do I use this to generate electricity? What are the parts I need, and how does it happen? That's my job today to get across to you. How do we go from this tiny little reaction, which gives off a tiny amount of energy, to generating the lights that are on and the smart board that's working right here in front of you? Let me show you. You need several parts for a nuclear reactor. All right, you need about 5 parts, bare minimum, to get a reactor going. So if you want to make one in your basement, you're going to need at least these 5 things. Okay, Jared? Pay attention. Jared is planning on powering all of Berwick from his basement with his homemade nuclear fission reaction. And by the way, you're going to find when you write this down, I do actually want you to write this down in your notes, Roman numeral 10, nuclear reactors. And then here's the crazy part. Here's all you're going to write after that. See the packet. You can put those notes away now. Because the rest of the time, I'm going to have you guys, and I almost never do this. I could say I never do this. I never give you a packet like this with all the information, all the notes already written out for you and everything you need to know. I have done this in this case. I have a little bit of time here. I can take this to explain it to you. Look, when you go off to college, you're all watching up here. Unfortunately, this is another perfect example of one of those ways we misuse technology. Okay, and we do. Professors, in hopes of being better professors and teaching better, spend a lot of time. Teachers do this. High school teachers do this too. I do it. We spend all this time making up these grand notes, and we're very proud of them. So we put them out there, and we put them online, and we put them in packets, and we hand them out to you. So you never even have to come to class, and you never even have to take notes. And that's a real danger, because if you're not, I just saw it last period, and I'll probably see it this period. As I'm talking today, without having to stop every couple of minutes and write something down, your attention wanders and wanders, and pretty soon you're sleeping. And that happens, okay? That's a very big danger. Many of your college professors will go off, they'll give you your notes. Hey, my notes are all online. You need them? Look up there. So all of a sudden you stop paying attention to class, you stop going to class. Just because all the notes are there, people, doesn't mean they were explained to you, doesn't mean the examples were done for you, all right? So I need you, when you have a packet like this where the information is already there, and I'm doing this today on purpose. There's actually another reason I'm doing it, not just to warn you about that. The reason I'm doing it for this is there are about, I don't know, 10 graphic pictures in there. Not graphic pictures, as in like, graphic, like violence. But 10 graphics in there that you could not draw on your own, all right? They had to have been given to you, okay? So that's why I'm giving you this packet. But there's also the notes are in there too. So you need to still pay attention, even though you're about to put away your notes and just be looking at the packet, all right, which has on the first page this information. Let's take a look at it. The basic components of a nuclear fission reactor. Okay, now don't read ahead. Just try to watch with me. Okay, take a look. I think everybody would probably get the first one. You got to have a fuel. You got to have some uranium-235 or plutonium, uranium-238, plutonium, thorium. You got to have something that is fissionable, that breaks up and gives off energy, okay? And it must be able, and I forgot my D there, it must be able to produce and maintain a sustained chain reaction, okay? Turns out that uranium-235 is much better at this than uranium-238. That's why we enrich the uranium, like I said the other day. All right. So you need a fuel. No surprise there. Well, what else do I need? Well, I need a moderator. What's a moderator? A moderator is that thing that slows down the neutrons. Fast neutrons aren't going to do this very well. I need that uranium-235. That's what I'm going to be talking. I'm going to use. By the way, plutonium is used in breeder reactors. We're going to talk. I'll just mention them briefly today, but I'm going to talk mainly about uranium because it's used in most of the reactors today. Most of the ones we have in the United States, certainly. All right. We need something to slow down those neutrons. They're moving too fast. What's a great moderator? Well, it turns out there are several moderators. There's carbon. That's a really good moderator. Water, and even heavy water. Now, somebody raised their hand at this point in the air class. They asked, what's heavy water? Anybody know? Water with an extra hydrogen would be H. Oh, no, I want green. Water with an extra hydrogen. I want green. H3O. We know what H3O is. What's H3O? They're what? Hydronium ions. That makes up an acid. Nope. Heavy water is not H3O.
Is it carbonated water?
It certainly wouldn't be carbonated water. That would be with carbon dioxide, and that's just soda. No. Heavy water is H2O. Water is H2O. They're both H2O. What do we know about H? Maybe from way back in chapter 3 or 4. And what are we talking about now with the nuclear chapter? Begins with an I.
Isotopes.
They have multiple isotopes. Actually, there's 3 isotopes of hydrogen. Most of it is hydrogen 1 with 1 proton and 1 electron. And that is the hydrogen that makes up water. Most of water, 99 point whatever percent, 90-some percent of water. The water that makes up heavy water looks like this. It's got 1 proton. That's what makes it hydrogen. And it's also got 1 neutron. And it's got 1 electron. Okay? So basically, the heavy part comes from the fact that this hydrogen is heavier than that hydrogen. And the reason you would use heavy water, by the way, Canadian power plants use heavy water for a lot of theirs. If you remember, in our water video I showed you from Modern Marvels, it talked about that. You can extract it's called deuterium. Protium is the major isotope of hydrogen, but deuterium has 2, a mass number of 2, 1 proton, 1 neutron. And you don't need to write this down. I mean, it's not important. I mean, it's kind of important, but it's not important for the test. What's nice about heavy water is it's a better moderator because it doesn't absorb neutrons. Regular water will absorb neutrons, and what's that going to do if it's absorbing neutrons to the reaction? Yeah, it's not necessarily stop it, but it's certainly going to slow it down. All right, so if it's absorbing too many neutrons, it will stop it. Right? Okay, so good enough. Carbon's a problem. We're going to find that out. Remind me if I don't mention it. I think I will when we get to the Russian reactors. The actually Soviet reactors back when it was the Soviet Union. The Soviet reactors use carbon as a moderator. We use water as a moderator, or heavy water. There's a big difference between those two. And the difference can be summed up in one word, Chernobyl. All right, we'll talk about that. The difference between Chernobyl and 3 Mile Island. There's a big difference there. All right, we'll talk about that in a little bit. So we need something to split up and give us energy. We need something to slow down those neutrons. Okay? We need to control this reaction. This reaction is going to get out of control very quickly. Think about it. If I let a chain reaction, you saw what happened when we threw a ping pong ball into that thing. The whole thing went crazy. 1 ping pong ball sets off 2, boom, it's going to go crazy eventually. I need control rods. Control rods basically contain boron or cadmium, which absorb neutrons very well. And they absorb neutrons, which would do what to the reaction? What would that do? Slow it down. So further in, I put into the core these boron and cadmium rods. The slower the more neutrons are absorbed, and the slower that reaction can control it. So I'm generating heat, but I'm not generating so much heat it's going to get out of control. Be a runaway chain reaction. I need control rods. So Jared, you're building that in the basement. Don't do it without the boron Okay, or you'll be a stupid moron. You also need a coolant. You're generating a great deal of heat here, people. You better have some way to dissipate that heat. And you also, this coolant actually serves usually two purposes. One, to cool down that core. If it gets too hot, it's going to melt. If it gets too hot, it's going to get out of control. Okay? But the other reason is we need to boil water. Okay? We need to create steam and get energy from this by driving a turbine, which I'm going to talk about right now. How exactly does that turbine work? Let me show you. This is what the coolant does. Actually, you know what? I'm going to save that. No, I'll do it now. Let me show you. The water, how do you think they make electricity, by the way? How does that power plant manage to turn these lights on? By just having a fuel get hot. Well, it can't do it by just having a fuel get hot. Let me show you what it has to do. This is what's up there. This is a AC generator, basically. All right, a turbine, kind of like a turbine, and I've got it hooked up to a light bulb. Let me switch these around here. I got it hooked up to a light bulb. It doesn't matter which way I do it, by the way. All right, just want to be able to see it. Okay, and if I turn this, what this is these are they look like magnets, don't they? They are. They're magnets, and inside of there is a coil wrapped, very thin coil wrapped around a spool, basically, a coil of wire. Now, the reason this works, you got to take EM to figure out from physics. Mr. Schrader's class to explain all this to you. I'm not going to be able to explain it. He's going to spend months talking about electricity. Well, more than months, and the whole class is on electromagnetic. Yeah. All right. But if I turn this coil in this magnetic field, what it does is it generates a current, an alternating current. It moves electrons. Watch. See that? See it flashing almost? See it flashing? Right? Now, if I do it fast enough, it's almost a continuous light, isn't it? Right? Okay? And that is an AC generator. This is not exactly, but it's very similar to what they have up at the power plant. All right? I took a class at the power plant many years ago. It was an actual college class from Bloomsburg for 3 credits. It was held at the power plant. So we met every day inside their training centers, and we walked around all the different parts of the plant. One of the parts of the plant were the turbine, where all the turbines are. You know what? This is basically the same design. All right, it's a magnetic field and a coil of wire, and it spins. You have to spin it. The turbines on that floor were about the size and mass of a school bus, spinning inside of a magnetic field and generating electricity. And there wasn't just one turbine, but multiple turbines there. What's the point of the coolant? What's the purpose of the coolant? My arm. What my arm is doing here is what the steam does as it goes past the turbine. Fans of the turbine, it pushes it. Pushes those fans, turns it in a circle, rotates it, generates electricity, which then goes out to all the homes around it. Okay? Weird part about this is they don't just have big magnets up there. Mr. Schrader told me about this. I was unaware of this. Actually, I probably was when I took the class, but that was so long ago I forgot. Fact is, these electromagnets they have up there actually have to have a separate source of energy to power them. All right? And so that's why everything's interconnected. These magnets aren't just magnets up there. They're electromagnets. They're generating they're being produced from someplace else as our plant turns this and generates electricity to put out to somebody else. And that somebody else may be another power plant that needs to generate electricity for their electromagnets. It's kind of crazy. But they're all interconnected like a web. So it's not like our energy comes from just that power plant up there. It comes from other power plants that help generate this magnetic field as well. All right. Let's get back to the last one. Okay, so the coolant not only cools it off, but also drives the turbine, spins the turbine that generates electricity. You need one more thing, Jared. You need a radiation shield. Or you're not going to be doing in their basement very long. Neither is your cat or dog or anyone else. They're going to be dead. Without a radiation shield, you don't have a cat? You have a cat?
No, I said I'm pretty sure she can survive.
Yeah, well, a cockroach might, but I don't think the cat's going to. So the cockroaches are okay. There's the things that are going to make it through the next nuclear fallout. All right, the radiation shield, turns out, obviously you guys probably know lead, very dense material. It's a great radiation shield. So is concrete, pretty good. Those walls up there at the power plant, there are 6 8 feet thick. I mean, they're very, very thick walls to protect us from that. But the best, one of the best ways to protect yourself from radiation, water. I also, like at that class, and I know Spencer in the air class went down to Penn State's reactor. I could stand on that floor, look down into the water, all right, where the fuel is stored, very radioactive. If I were to get close to that fuel, kill me instantly. I mean, I'd be dead by the time I reached it. By the time I were able to touch it. I couldn't touch it, I'd be dead. All right, very radioactive stuff. But I could stand there, look down into the spent fuel pool, and I could see it and not really get a whole lot of radiation from it. Why? Because water absorbs radiation very well, all right, and it's a very good shield. And in fact, up until about 8 years ago, I think, all of the fuel on site, these pellets come in big long rods. So the time that place opened in like 82 or whatever, till sometime in the 2000s, all of the energy they generated from this fuel. Remember, these little pellets, I said this the other day, they're about a ton of coal's worth of energy. Well, they don't last forever. Eventually, the uranium's gone. I mean, it's been broken up, and so you have to you take them out, the spent fuel. That's what they have those outages for, right? You know what an outage is up here? I mean, I'm sure many of your parents maybe even work the outage. All right. Well, they have to take those certain ones out, put them in a spent fuel pool. Now, they're still very, very nasty, much worse actually afterwards for how much radiation they have because of all the decay products, and they're very radioactive. But up until just recently, all of that was stored on site, was stored in that fuel pool, spent fuel pool. Now they have other containers that they store them in. And because there's decay heat, they have to have special containers that are allowed to dissipate that heat. All right? But that's where they were all stored, just in a swimming pool, basically, a big swimming pool. I mean, it was huge, and a lot of water in it. Water was very clean because no bacteria could live in it. Why not? Yeah, the radiation. Water looked clear as a bell. No mold, no bacteria, nothing. You look down into it. It's pretty cool. Okay. So those are the 5 things minimum you need to make your own nuclear power plant. All right. Now, I need to spend. And so, Jared, you got your work cut out for you. All right. I need to show you now. I'm going to show you some graphics. These are not on your paper. There are some other ones that are, and we'll get to those. Check this out. All right, I want to explain what's going on in this neat little graphic I found online just last year, first time I used this one. It's pretty cool. Look what happens here. Let's trace what's going on. This is basically the design. That's my house right there. Okay? Notice I'm turning the lights on. I'm coming home. And I'm home. Hi, honey, I'm home. Yeah, there. Now I'm going to bed. Watch. Time to go to bed. Oh, good night. That's my whole life. It's just this basically sums up my entire life. Let's watch what's happening here. Okay? Let's start with the nuclear fuel, which is over here. This is where the core is. We call that the core where the nuclear fuel is. It's also where the control rods are. And we call this the primary containment vessel. Okay? Primary being the first containment, first way you contain the radioactivity. All right, so let's look what happens here. The core gets hot, symbolized by this little orange and red stuff here. Okay, core gets hot. And it gets so hot as water is pumped into it to cool it off. What does it do to that water? It turns it to what? Steam. If you can't notice from where you are, these are little puffy clouds of steam coming up. By the way, that steam is so hot, it's invisible. You know, we think of water vapor as being clouds, but actually, this stuff is so hot. And this cool water coming in is really hot. It's just nowhere near as hot as it's going to be. All right? So anyway, this steam goes up here. It's really hot steam, has a lot of pressure behind it. And what does it do? It goes to my turbine. And it turns this guy, right? It's not working because I knocked the thing off. Turns this turbine. The turbine generates electricity, and I turn my lights on and it works. Okay. What happens after that steam goes past the turbine? Well, it's done some work. It's probably not quite as hot now, but it's still pretty hot, and I'm going to need to cool it off. I cool this off and turn it back into a liquid by pumping water from the river, right? This is the Susquehanna down here. He pumps the water in here, all right, and that cool water is in a separate loop. The water in here never touches the water here. And that's a good thing. Why is that a good thing?
Because then the river is
Right, because the river would be contaminated. This water in here is floating around with all that radioactivity. This water's nasty stuff. We don't want to touch that. So it stays separate. This loop here stays separate from this one here. If they were to touch, that would be a bad thing. We'd be then sending radioactive water back out to kill the fish, right? All right. By the way, once it cools it down, that cooler water now goes back to my core and gets heated up again. It's a nice little loop. Drives the turbine. Turbine spins, generates electricity. Electricity flows to my house. The whole thing goes over again. Yeah.
What about like the steam from?
Where does that steam come from? Well, from this water here has to be cooled before it goes back to the power plant. Okay, I'm sorry, before it goes back to the river. So that's what they do with this water. How hot is this water going to be after it goes through this loop? It's very hot. So what they do is they don't want that water going back to the river like 40 degrees warmer than it was, because it's river fish don't like they like where they are. They like the temperature they're at. So we don't want to do that. So we put in the one part that's missing from this would be the smoke, the big stacks over here. And everybody calls them smokestacks, and of course they're not. They're just steam coming out of there. So this hot water that comes after it's done its job of cooling the stuff down goes into here. It rains in there. You ever drive by, see it rain in there? What's that? It's just cooling down the water. These are cooling towers. That's what they're called. Cooling towers. Then it goes back to the river. Okay, so that's the one part that's missing from this loop. Got it? All right, got it? Now I want you to look at this. I paused it. All right. Notice the radioactive water makes it all the way outside of the primary and even the secondary containment vessel at different parts. That water that drives the turbine, that's going to be contaminated, and it gets outside more places in a plant like ours at Susquehanna. Well, this is 3 Mile Island. Well, it looks the same. Is it the same? Look at it closely. Is this the same? No. There's a separate loop. This is a separate pressurized loop in here that contains all the radioactive crap. Okay, is in there. Then it's got this loop here. Let's see if you could all see it. So you got this loop. This is the radioactive stuff. We'll make that red. This is radioactive, and it's going around. This is not. I'll use black for this one. All right? But that's what drives the turbines. Now I don't have a turbine being driven by water that should be as radioactive as it was for the Susquehanna time. And finally, you've got this loop, which is river water, okay, going back to the water. So there's another layer of removal from the radioactivity. As a matter of fact, before the accident at 3 Mile Island, a reactor, a pressurized water reactor, which is what this is. Actually, if you were to stand outside of it or walk around outside of it, you're going to get less radiation from it because the radioactive parts and water don't really leave the secondary containment vessel like they do in the ones we have here. In Susquehanna, they actually leave and go further outside the plant. Not outside the plant, but outside the containment vessels. Okay? Still, if everything works correctly, you're not sending back radioactive water to the river, in either case. All right, so you get the idea? Okay, now, I'm going to talk about, this is the boiling water reactor. It's the same basic, this is the ones I have for if you were to flip through, you'll see. And it's the same basic idea as what I just showed you, right? I mean, this is the water from the river, cooling down the water that's driven the turbine, which goes in, boiled and pumped, boiled, turned to steam and drives the turbine, cools down, there's your loop, and of course it goes outside. Here's the same one for the pressurized water. You have a separate loop, you have a separate loop here, and then you have this loop here, and then you have the water from the river, right? Just like I showed you, only I think the other one was better because it kind of had the flow going through it, but these are the same basic ideas. Now, I'll just talk very briefly about the fast breeder reactors. They actually are interesting because they actually can generate fuel while as part of their waste, and they can reuse it. They can use plutonium and things that we can't use in our reactors. These are used very much in France. France has a lot of its electricity generated by nuclear power, a great deal of its electricity generated by nuclear power. The problem with this, the high heats of this require, water's not good enough for a coolant here. They actually have to use liquid sodium to cool this guy down. And that's, I always scares me. You guys know what happens when sodium hits water, right? Remember in the fume hood? Yeah, it blows up. It's just a regular explosion, okay? And eventually you do need water because you need water to be boiled and turn to steam and drive the turbine and then cool down. So, I mean, I never, but still, these are very, they've tried and true, tested, and used by France a great deal, breeder reactors. And then we also have, and this is the biggie I want to talk about a lot right now because it's going to be one of the major accidents that happened. This is the Rbmk Russian reactor, okay? Now, I want to go back for a second to the, keep this one open though. Keep this one open to your paper. Let's go back to a second to ours. What's the worst thing that I could do? All right? What's the worst thing that I could do? Here's my cooling water coming in. Here's my core that's really hot, okay? And I'm boiling it, turning it to steam. The water turns to steam, drives the turbine, and then turns back into cooler water. And then starts to lube over. What's the worst thing that could happen to this power plant? Shut the water off. Exactly. I shut the water off, I got a problem. I can no longer cool that red hot core. Okay. So what do? I have. You ever notice there's a huge pool of water outside the power plant up there? What's that pool for? Well, it's a reserve, just in case there were a blockage or the river. You know, some terrorists decided to blow it up. You know, a pipe, one of the intake pipes from the river, whatever. You've got a way to cool the plant down there. But let's say that broke. I mean, there's just no way to get water to that core. Uh-oh, Hiroshima, right? Boof, gonna blow up. No, actually not. This is the crazy part about this. Is the best part about this design. All right. Now, I'm not saying bad things won't happen, but I am saying you cannot get Hiroshima or Nagasaki or a nuclear bomb going off by cutting the water off of this power plant. Won't happen. Because what have I cut off if I've cut off the water? What else have I cut off? Looks like I got to go back a little bit. What else have I cut off? The moderator. What's the moderator in our power plant? Water. Water is what slows these neutrons down. Water slows these neutrons down. Okay? If I take away that water, if I stop, I interrupt the flow of water to this guy. If I stop that water, the nuclear reaction, the fission reaction, the chain reaction stops. Say, well, how could it? That's nice. How could anything ever go wrong? Well, things can still go wrong. First of all, there's no longer a nuclear reaction going on here, but there's a heck of a lot of heat still in there, decay heat. Guys that are these other nuclides, as they're breaking down, are giving off a great deal of heat. So much heat, if they're not cooled, they will melt the stuff that's in there. That's exactly what happened at 3 Mile Island. Remember at the end of 3 Mile Island, the video we saw? They put a camera down into the core, and the camera, 1 foot, 2 foot, 3 foot, 4 foot, the core's gone. Like 4 foot, like the first third of the core or more, 40%, I think. You'll have to look it up when you're doing your thing tomorrow. But a good percentage of the core was melted by that decay heat, because that's exactly what those people did. Those engineers, those operators, thought that there was too much water going into that core, into that vessel. So we know what they did? They stopped it, cut off the water. All right, because they didn't realize that there was a valve somewhere in here that was stuck open. And water was just leaving and leaving and leaving. Now the plant knew it. The plant, get me some more water in there, it's too hot. They said, we know better. They stopped it. What happened? All the water left the core, pretty much exposed the core. And melted all of this stuff in here, which just, you know, it was so hot for hours, this stuff was just drained of water. It just melted and it all settled on the bottom of the vessel, the primary containment vessel. Now, that's where the China syndrome comes in when you heard about that, right? All right. Basically, they did the worst case scenario that you could do to this plant. They cut the water off for a fairly long period of time. And they stopped. What they basically tried to do, they didn't do it on purpose, but they tried to make what they would call a China syndrome. And of course, the China syndrome says that, you know, this stuff is so hot, it's going to burn right through the bottom of this vessel, then right through this, and right through that, and right into the ground, and eventually hit groundwater and be this huge, massive explosion and kill everybody around here. As to talk about the one of those guys on the movie, you know, make an area the size of Pennsylvania uninhabitable for millions of years. That was actually a quote from the movie. You know, an area. Now that's nonsense. I mean, it is. They did it. They did that right here. That's exactly what they did. And had they let it go without ever putting any water in there, I mean, it's certainly possible that it would have, you know, leaked out, maybe gotten through the primary, maybe even gotten through the secondary. But an area the size of Pennsylvania being rendered permanently uninhabitable, not gonna happen. All right. All right, this is not like the acid from Alien. It just keeps burning. You ever see that movie? It just keeps burning through everything, okay? Eventually, it's going to, you know, cool down. It's going to spread around. Now, does that mean that people wouldn't have been hurt and killed? No. But there's a big difference between having radiation released and hurting people and rendering a size of Pennsylvania uninhabitable for millions of years. People like to scare you with stuff, and that's just a little nonsense.
What happens if there is too much water?
Too much water? Well, yeah, they didn't want too much water in the core because the pressure would build up and it could crack the vessel. Okay, so that's why they cut off the water. But they didn't know that there was a valve stuck open because the light wasn't flashing here. You're going to read about it tomorrow because you're going to do this on your own. Okay. All right. So, but here's the key. I kind of got off on that little tangent, but here's the key to this, guys. Listen, if I cut off the water, I cut off the moderator. Not just the coolant, but the moderator. So the nuclear reaction, no one's going to argue with this. The decay heat may or may not burn down to China. Not. But, you know, that's, you know, China syndrome. Okay? But one thing everybody agrees on, there's no longer a nuclear reaction going on. It's not nuclear because the neutrons aren't being slowed down enough. Here's the problem with the Rbmk reactor. What did the Rbmk use for a moderator? Graphite is this moderator. And you know what graphite is? Their name for graphite? Carbon. Very good. And you know what carbon does when it gets hot? It burns. And that's exactly what they did. All right? There's a long reason why they did it. You'll have to read, again, you're going to do the research on this too. But eventually, they burned this core, and it burned for days. And it gave off massive amounts of radiation, killing people. Not like 3 Mile Island, where a very small amount of radiation was released because of some water that was not deliberately, but on purpose. It was, you know, to relieve the pressure, was left out into a floor of another containment building. But they actually burned this core, and nuclear fissile material was just thrown all over the world. The world, because this plume of radioactivity made it all the way across the ocean and back, and the United States was able to pick up radiation from Chernobyl. Okay, it was a nasty accident. It killed people. How many? That's what you're going to look up. Very interesting how you're going to get different answers to that question. All right, but it killed people, unlike 3 Mile Island. All right. It killed people from the nuclear power plant. And this is a nasty, I mean, well, not the main reason. There's a lot of reasons. You're going to read about a lot of them. But here's a big one. Could this happen here? And the answer is no. If you cut off the water to this plant, you have not cut off the moderator. So that can still keep going and get even hotter and hotter and hotter. If you cut off the water to our plants, you've cut off the moderator. Cannot. I'm not saying this as, oh, well, you know, you're some tool of the nuclear power industry. It can't be a nuclear bomb. All right? It can't get out of control in that way. It can cause problems, just like this guy caused problems. Way worse here. All right? It can cause problems. You can release radiation. You can get a plume of steam that will go off that's radioactive. I'm not saying that, but it can't. What happened here will not and cannot happen where we are, because it's not going to get out of control in that way. You still have the moderator here. Nasty problem with this one. You're going to look up all three of these. I'm going to pause the thing now, but basically that's what you're going to do next. I'm going to give you these papers each day now for the next like 3 or 4 days. And we're going to do our own research on these